it's called UC Barroso physics in this kind of systems, and think about novel idea of novel qubits based on such levels. Okay, so this is the program of the talk. First, I will tell you a bit about the basic physics of a quantum dot coupled to a superconductor, what we call a superconducting Anderson model or superconducting quantum dot model. And I will mention briefly a collaboration with the Delft team, where we were, their experiments, I contributed with some theory. They were able to demonstrate the physics of these singlet doublet transitions, these parity crosses in the quantum dot by using microwave experiments, using a quantum dot-based Josephson junction, and eventually demonstrating a spin qubit living in a superconducting circuit, living in a Trashmont circuit, and strongly coupled to the Trashmont degrees of freedom. Using these ideas of the quantum dot Josephson junction in a superconducting circuit, we can start to think about a novel qubits based on such quantum dot. And there are kind of two main routes. The first one is the non-Majorana route, which I won't discuss today, which is how to improve this, what we call anti-F spin qubit, how to improve the properties of this spin qubit in the superconducting circuit. And here we have a few projects, open projects, or almost finished papers. This is a paper where we discuss how to improve the properties of an anti-F spin qubit in a Flaxonian geometry. We are about to finish this. Also, how to go to hole-based semiconductors, how to use germanium quantum wells, and to use the properties of hole spin qubits to improve the properties of these systems. And this is mainly based on collaboration with Yorgos Katsaros in ISTA. And then we also have some activities in Gatemons, in the ultra-strong coupling limit, together with Eduardo in Madrid in his lab. This is not Majorana. I won't discuss this today. I will mention briefly how to go from single quantum dot in this kind of systems to arrays of quantum dots, and how to actually mimic the physics of the Kitaev chain. And this is when we come back to Majorana. So we were trying to implement Majoranas. We realized that, hey, quantum dots can be relevant. You can have all this physics of Andreev levels in quantum dots. But now, since the last 2-3 years, we have been able to understand that you can actually use quantum dots coupled to superconductors to mimic the physics of the Kitaev chain, to actually tune arrays of quantum dots to the Kitaev limit and to actually construct Majoranas out of them. I will mention this recent paper from Delft. Again, we contributed a bit with theory, where they demonstrated single-shot parity readout. So actually being able to read out the two possible parities of the minimal Kitaev chain. Some theory we are doing around this, and actually on Monday they uploaded a paper in ConMat where they actually demonstrate for the first time a qubit based on parity with this minimal Kitaev chain.
Is it really a qubit or
It's a qubit.
So that just parity time?
No. Here they measure the parity time. On Monday they actually demonstrate Rabi oscillation. So I would say they demonstrate rotation. Parity
between the parity and configuration.
Rotation between the two parities of the segment in a junction configuration. I can mention that. So I think it's a qubit. Okay, we can discuss about this. You are not convinced.
I want to know the details.
Okay. So all these ideas about these hybrids are here in this review paper that we wrote together with some friends here. So if you are interested, please go to this archive where you can find all these details about the hybrid. Okay, let me go quickly through this. So you all know about the Trashmont, of course. So you have a Josephson junction, which is shunted by a capacitor. This is kind of the basic building block of all these fancy quantum computers. But the idea here is going to be replacing this Josephson junction by some SNS junction, some Josephson junction based on semiconducting segments, and in particular to exploit the properties of quantum dot Josephson junctions. So in particular, we want to use the properties of these subgap levels living inside the gap of the superconductor and being able to manipulate these degrees of freedom to build qubits out of it. All right, so the physics of this quantum dot coupled to the superconductor is essentially the physics of an Anderson model, an Anderson impurity model, for those of you who know about this physics. From the point of view of the quantum dots, this is just a quantum dot in the strong Coulomb blockade regime. You have a superconducting states. You can still have some kind of Kondo processes where quasi-particles in the superconductor can or try to screen this spin degree of freedom, and these are the famous Jussi-Barushinov singlets. So Jussi-Barushinov singlets are nothing but Kondo-like singlets in a superconducting setting. This is kind of complicated problem. You have a strong Coulomb blockade, you have a superconducting correlation, you have Kondo-like physics. So at the end of the day, you have a phase diagram like this, where depending on parameters, you can be in a doublet phase, where you have essentially a free spinning impurity. This is when you have odd fermionic parity in the quantum dot. This is the level position of the quantum dot. This is half filling, so you have this kind of dome shape here, and this is the coupling between the quantum dot and the superconductor. So when you increase, you go up in coupling, eventually you enter this kind of Kondo-like or Jussi-Barushinov-like singlet. This is when the charging energy, or HABRU, depending on your language, is much larger than delta, than the superconducting gap. You can actually have another regime where you can have Andreev levels. This is when the charging energy is much smaller than the gap. This is when you actually induce superconducting correlations locally in the quantum dot, and you go all the way down to the Andreev level solution, which is actually without any interactions. So there is actually a very nice paper by Pascal where they discuss this so-called infinite gap limit, where you have this kind of BCS-like solutions, these Andreev levels in the proximitized quantum dot. But here the parity is even. Here you have singlets. Here the parity is odd. And every time you cross this boundary, this is when TK is of the order of the gap, more or less. So every time you cross this boundary with parameter space, when you move in parameter space, you change from even to odd to even. So you have parity crossings in the system, meaning that you can have excitations which live at zero energy because the two ground states are degenerate along this line, which connect these two parities. So essentially, you can have zero energy crossings in the system every time you cross this boundary. Already for a single quantum dot, you can have the zero energy crossing. All right. So you can actually, there are many experiments doing tunneling spectroscopy in this kind of quantum dots, but you can actually go a bit more sophisticated and try to do this, try to explore this physics with circuit QED, with microwave experiments. And this is part of the thesis of Arno and Marta Pita, who were PhD students in Delft. The idea is, you have a transport circuit, you have a squid to have flux control, and you replace one of these junctions by one of these quantum dots. So this is my, simple-minded theory cartoon for this quantum dot Josephson junction in real life, and you want to explore this phase diagram, right? To either with flux or with gates in the quantum dot, you want to actually explore this phase diagram. As I said, this is my simple-minded cartoon, but in real life it's much more difficult, of course. So, you have a tiny quantum dot junction with an indium arsenide wire. You have gates where you can tune this quantum dot junction. This goes here, in this loop, where you have this kind of a squid loop, and this goes there in a, circuit QED-like setup where you have a resonator. You couple this to a resonator, and you do a microwave readouts. Okay, let me go quick here. Essentially, you can map all the phase diagram of this quantum dot. This is actually experimental data. This dome physics you can map by doing microwave readout with circuit QED. Okay, essentially you look for microwave resonances. and you can map whether you are in a singlet or in a doublet. The sharp drops occur every time you cross the phase diagram. So you can map the full phase diagram. This is experimental phase diagram, either at phase at flux 0 or pi. You have this kind of chimney-like shape, which is was also predicted by theory. So you have very good agreement with the theory. Actually, you can map the full phase diagram with microwave readout, and you can actually map the theory. So this is actually a good Anderson model, a good superconducting Anderson model in this kind of circuit. You can put yourself in a doublet ground state, either, as I said, with gates or with flux. You can tune the system to be in a doublet, so you can tune the system to be in a spin state. And now you use the fact that you have a strong spin-orbit coupling in the system. This is a semiconductor. So if this length of the quantum dot is of the order of the spin-orbit length, you can actually have a spin-orbit splitting in these branches. And here, this is data, again, where you can see very nicely, these are transmon lines, microwave transmon lines, which are spin resolved even without any Zeeman field. And on top, you see some theory plots that we did. You put some spin orbit coupling in the Anderson model, and you see very nicely two spin lines, spin resolved lines, even at zero magnetic field for this kind of transmon circuit. So now you can use these two spin degrees of freedom to demonstrate a qubit. Okay, and this is what they did. Well, we can do a bit of a theory. We can end up with a simple model for this junction, essentially cos phi, which is the part coming from the pi junction, and this off diagonal mixing spins coming from a spin orbit coupling. And all these parameters have some microscopics inside. All right. You can drive these branches and demonstrate, either versus flux or versus Zeeman. You can drive this qubit, so you have very nice rabbi oscillations. You can demonstrate a strong coupling between the transmon and the spin. Let me skip this slide. You can demonstrate a strong coupling. So James Cummings physics between the transmon, the plasma modes of this transmon, and the qubit, the spin qubit. You can demonstrate very nicely strong coupling between these two qubits. James Cummings like coupling, which actually depends on a spin orbit coupling. And again, we can do a bit of theory and understand the system very well. Okay, this was just to illustrate the idea that these junctions can be controlled, can be tuned to the situation in which we have a single spin, and we can couple this single spin degree of freedom to this transmon circuit. This is not the best qubit ever, of course. So, this is a spin qubit in an indium arsenate. So you have nuclei, you have hyperfine coupling. So in particular, T2 times are very short. So this I mentioned in the introduction, there are ways of improving the coherence properties of these qubits, like putting this quantum dot junction in a fluxonium-like circuit, what we call the IPA qubit, the inductively protected Andreev. So you put this in a fluxonium-like profile, circuit, and essentially you can separate the spin branches into different phases. In a double well fluxonium potential, you can put each spin in a different phase, in a different minimum of the Josephson potential, and then you can actually strongly suppress the overlap between the two spins. This idea, or you can go, just that we had some nice talks about high kinetic inductance superconductors like Graal. You can go to these devices based on germanium quantum wells and demonstrate a very good proximity effect with Graal, with these high kinetic inductance superconductors. And these are experiments from Yorgos Katsarov's lab, and you can actually demonstrate very nice properties of these quantum dots in these Graal superconductors. And in particular, we are able to describe physics coming from holes in these germanium quantum wells. and we are doing some theory on the what we call the Andreev Hall spin qubit. So taking advantage of heavy holes and playing with the properties of heavy holes, you can actually improve a lot the properties of this spin qubit. All right, let me go quick because this is getting late. So now the idea is, okay, I already discussed how to isolate a single spin in a transmon circuit, how the transmon is spin split. So now the idea is to extend this to arrays of quantum dots, like the minimal array would be 2 quantum dots separated by a superconductor. So this is like a Lego block. You have quantum dot 1, quantum dot 2, and you have a superconductor in the middle, and you can actually mimic the properties of a key-type chain. So the idea is to go from spin-resolved lines to parity-resolved lines in the transmon, and actually use these parity states from this key-type chain as a qubit. And this is actually this idea that we have for this European project with, we call it a QKIT, or KITMONs, key-type transmons, and this is a Pathfinder project coordinated by Rigid and Christian Andersen. So they are making great progress in doing this, in implementing this kind of key-type chains in transmon circuits. All right, so I'm about to finish. The idea is now to back to Majorana. Now you have the superconducting segment here, and this superconducting segment is again a proximitized segment inside, this kind of device where you have a nanowire, or here you have this proximitized segment. So this proximitized segment has Andreev-Bohm states, and you can actually use the Andreev-Bohm states in this segment here or there to actually mediate coupling between the quantum dot 1 and the quantum dot 2. This coupling can be single electron coupling, like this kind of coupling. You have one electron back and forth between the two dots, and this is in the key-type, just the standard hopping in a tie-binding language, right? T, C plus 1, C plus C2. The single electron tunneling back and forth between the two dots. This you can mediate with the Andreev level. You can tune this in a very precise manner. Or you can actually take the Cooper pair here in this segment and split it into electrons, one in quantum dot 1, the second electron in quantum dot 2. So you induce pairing between the two quantum dots, which is the second term in the key-type model. This is pairing, spinless pairing between quantum dot 1 and quantum dot 2. So you can tune these two processes, the single electron tunneling and the pairing, in this minimal array. And you can demonstrate, and this was a paper 2 years ago from Delft, you can actually tune the system to be in the sweet spot of the key-type model where T equals delta, where the single electron tunnel equals the Cooper pair splitting, and then you are in this, again, this is parity degeneracy. You are in this cross where even ground state is degenerate with odd ground state. And precisely at this point, which is a sweet spot, is a fine-tuned sweet spot, you actually get a zero energy peak, a Majorana mode. So Majorana modes here are clear. I mean, you really tune them to be where you want them to be. And experimentally, you actually can tune this in and out in a very precise manner. How much time do I have? 1.5. Okay, so it's okay. So now these zero modes, as I said, are related to parity degeneracies in the system. So you have even ground state, odd ground state. When they are degenerate, you have a Majorana zero mode. So you can actually distinguish the two parities in the minimal key-type chain by doing quantum capacitance. So you can, for instance, by moving this delta, which is this common chemical potential, mu left plus mu right. So you have the left quantum dot, the right quantum dot, and you move this common chemical potential. You couple this to a tiny oscillating signal, like in quantum capacitance experiments. Like I can skip this theory we are doing. So, you know, you put some RF signal in the middle, so you shake a bit this middle bridge, this middle superconductor, and you can actually perform quantum capacitance experiments like people in qubits do all the time. So essentially the idea is that when you shake this middle segment, the capacitance of an LC resonator that you couple through this line is going to be slightly affected by these changes in the parity of the left chain. So essentially, you are sensitive to curvature of these levels, depending on whether you are even or odd. You can distinguish between the two parities because they essentially, in the simplest theory, the second derivative of this level, which is the curvature, which you can relate to capacitance, is going to affect differently the contribution to the capacitance that you pick up with this resonator. This is the same that people do in qubits. So at the end of the day, experimentally, you are able to see this kind of off-diagonal lines, which are related to the changes in capacitance, and you are able to distinguish between the two capacitance, the two parities in the experiment. You can do real-time readout. I can skip this. This is the full theory. You can do real-time readout of the two parities, and you can extract actually, parity lifetimes above 1 millisecond. So this experiment demonstrates that you have good control on the parity. Good control on the parities of the chain. They have very good lifetimes, so you can use these two parities to actually demonstrate a qubit out of them. And this is where I stop, because you all wanted to discuss perhaps this for this afternoon. It's a good discussion. On Monday, they actually put this paper on CONMAT in Leo's group, where they do some qubits. They seem to see some Rabi oscillations. So this is probably the first Rabi oscillation demonstrated in one of these minimal Tidal chains. Okay, we can discuss this. I'm asking. This between parities. So you have the two. You have global parity, which is conserved. So you have two segments, and these Rabi oscillations demonstrate that the inner parity on each segment changes. So you go from odd to even, which is global even parity. So this is Majorana mediated. But I can actually show you. We already did some simulation. Yeah, this is a Majorana mediated coupling between the two partial parities. So I believe this is a Rabi oscillation. With this I'm done, and thank you for the attention. Thank you.
Other question.
This is my question about this double quantum system, but if you have a larger one, in this type sweet spot, what is the Majorana localization length?
Very short, of course. Very short. Right. Of course. I mean, I'm not claiming that this is a topological system. So for this, how the original idea comes from Carsten Flensburg and Martin Leinze. They call it Pullman's Majorana. So of course, this is a segment. So you can tell from the geometry of the sample. This is a very short segment of a few nanometers. Right here, for instance. So, this is 200 nanometers. So, this is at the end of this quantum dot, at the end of the quantum dot there, you have the two Majorana. Of course, you can extend this idea to longer chains.
And then you have 3, and then the localization length will be 1.
Right. So you can actually improve the properties of your chain. And depending on the estimations, already with 5 dots or so, you can actually be in situations where the localization length is good enough to be enough.
It's kind of discrete system, right? I mean, if you have 5 dots, your localization length is in terms of.
Well, now it's a question. I think the main problem is in this system is the question of whether you would be able to, let's put it this way. So in the nanowire, you are kind of blind to global disorder in the chemical potential, right? So So you have some nanowire that you deplete, and of course you have some profile of disorder you don't really know, you don't really control. Here you substitute this by discrete disorder in the sense that each of these gates, when you tune the chain to be perfect, each of these gates is going to have some little disorder. So if you are able to control gate noise in a length which allows you to have good homogeneity, then you're good. If not, you are right. I mean, you have a discrete chain, everybody is fluctuating, and your localization length is going to be very, very short. So it's a question of tuning, I think.
Maybe there's one question. I'm a little confused by the experimental setup because you mentioned that it's quantum capacitance measure.
Yes.
But this is not really obvious to me because you have this. You have a superconducting loop in the system. This is inserted in the AC squeeze set.
No, but in this case, yeah, thank you for the question. Yeah, so I went too fast. In this second implementation, they do quantum capacitance. You could do this in a Josephson junction loop,
yes.
And then you could go to inductance and try to measure also.
The last experiment, there is.
I mean, in this experiment, what they do is quantum capacitance.
February, but the experiment online now,
the last one
with this the Rabi oscillations.
Yeah, but in the last one they don't do quantum capacitance as far as I know. So
but then I think the interpretation of Rabi oscillations for me, I'm not sure this is Rabi oscillation between two states, but this is obvious. This is really what you want. This is two parity states. This could be Rabi oscillation between two levels.
Good. Yeah. So yeah, thank you for the question. So yes. So what you have to show is that this is, by the way, this is related to your question. So you can do the full theory of dispersive readout either with quantum capacitance or with inductance, depending on your geometry, and of course you would have contributions beyond curvature, right? So yes. But in the experiment they did quantum capacitance. But coming back to the rabbi. Well, you have to demonstrate.
You have quantum jumps, but you don't have Rabi oscillation.
Right, but here what you have to demonstrate, or what I think they demonstrate, is that both the even and the odd even, when you are in a global parity sector, either even or odd, you have the two rabbi oscillation matching. And then when you tune one of the segments, depending on whether you tune one of the segments or not, you know when to expect rabbi oscillations only in the even or in the odd. So they do kind of sanity checks, like, this is experiment even, you have rabbi, even if you shake the dots in opposite manner. This is theory, we did some simulation. So you expect it kind of works. So at least for this minimal model. So
maybe I propose to keep the discussion going this afternoon, and actually it's your turn to speak.
Thank you.